Good morning, everyone. Welcome to the EasyPower Refresher webinar series. My name is Jim Chastain. I'm an applications engineer here at EasyPower, and we welcome one and all on this every other Tuesday brief discussion about some aspect of applying the EasyPower tools. We're talking today about specifically a fairly complex topic and how EasyPower deals with it, and it's a fun discussion any way you look at it. Before we get into the details, I do like to run a poll question and collect some feedback from everyone. So if you would please participate. First question is, on a typical system that you work on, what basic size or what's the most common size of VFD in your projects? And so there's no liability or obligation, but it helps direct the topic if we kind of know the perspective of the audience. So it looks like we're close to a quorum here. All right, thank you. Here's how folks have weighed in on this one. Looks like there's more leaning towards the heavy drive systems. The second question, how often is regeneration used or utilized in your systems or your typical design? This is one that I'm really curious about because in robotics, and we're using DC motors in the robotics drive systems, regenerative braking is frequently used for better position control. You don't want your robot overrunning its spot. All right. Here, how most heavily we're on the non-regenerative topic. And then the final question, how often do you need to control the frequency of the motor drive, the motor speed? Not just the speed, but the drive frequency itself. And this is the one that puts a kink in the discussion because it's a non-trivial solution. And I think what we're talking about is the EasyPower's ability to do a fairly decent approximation. So it looks like we have folks weighed in on this pretty evenly. And I do a thank you for participating. And again, welcome all for attending today. Hopefully we'll be able to share some information that's useful. So today's agenda is basically to touch on the VFD basics, and especially those that impact the frequency of the motor being driven, and then talk about how EasyPower deals with this. As we've kind of discussed in the past, there's basically three sections to a VFD controller. There's the rectifier, the filter, and then the output inverter. And it's this variable part on a variable speed motor that complicates the issues. One of the benefits of a VFD is the ability to improve the power factor the system sees from any given load, and we see that that's relatively simple in the home frequency, if you will, of the motor itself and of the drive system as far as improving the power factor. This becomes more complicated when we have a different frequency, and some of that is what's going to complicate the discussion going forward. Okay, so in a general sense, on a linear scale, work is a function of force and the distance to which it's applied. In the rotational world, torque is the product of the force times the distance applied, or the radius, and then the angle involved. And then power is the rate at which work is performed, so it's torque over time. With those basic parameters, if we use watts constant, torque times the RPM divided by 5252 gives us the horsepower. Now, if we look at the way a VFD works, we have a constant phase or constant part of the performance on the left of the curve, which is those frequencies which are below the main design frequency of the motor. So for a motor that's designed to work at 60 hertz, anything driving at a lower speed we have to adjust the horsepower to maintain the constant torque. And anything above the design speed, we're going to maintain constant horsepower, and then the torque will suffer. And so that ends up being a general rule of thumb in VFD controllers. Now, a lot of the magic that we see in a lot of the details we're trying to come up with in a simulator is based upon trying to simulate what's going on inside the VFD controller itself. So in EasyPower, the motor model for a VFD is based on the basic performance of a 100 horsepower motor. And in that, we're assuming that the motor load on the shaft is modeled as a speed squared. And in general rule of thumb, below 60 hertz, the VFD output power is approximated by the power at 60 hertz times the voltage per unit squared at the frequency we're trying to drive the motor. Above 60 hertz, the VFD output power flow is approximated by the power at 60 hertz times the frequency squared. So we're going to walk through a couple examples to show how Navid is already asking about DC motors. I may delay that one to the end. But yeah, we can simulate the DC motors with the VFD drive in EasyPower. Okay, so in the past I've talked about EasyPower Setup specifically for short circuit. So let's jump into EasyPower and see how this works. When we go to set up a motor, a basic motor in EasyPower, it requests the horsepower, and based upon that, we may have some ability to calculate full load current, or if we don't, it calculates the kVA rating for the motor based upon these other parameters. Now, these are default parameters that may or may not be true in every case, but they're a good general typical value. And to calculate short circuit, we need to produce a product of X over R that this particular motor presents to the system. And that's all that's required to do a short circuit calculation. Now, in terms of PowerFlow, we talk about the motor being modeled as the speed squared. Here's where that's handled in the PowerFlow tab. And so if we want to model some other parameter as far as the exponent, we could change it here. If I go back to the specification tab, it's relatively simple to make a VFD drive and assume that we're driving a synchronous, a condenser, a straight induction motor, or a DC motor. Now, I'm not going to spend, because I don't have any DC system set up, but if I drive a DC motor, I shouldn't even worry about that. I can go to my power factor, and I know in a DC motor, my power factor is going to be 1. And so with that modification, the tool will give me an icon then that looks different, and will assume the properties of driving a DC motor. Now, before I depart too far from this, back under short circuit, I also can designate regenerative or non-regenerative, and this will play a part in the short circuit. If we have a regen drive, we have contribution current back into an arcing fault. So let's see what my short circuit does for me. So based upon this being a regenerative system, during a fault on this bus 2, we'll see 481 amps contributed out of this VFD controller. If we go back to a database and make that a non-regen, and we'll see that we don't have any, and that's one of the benefits of a VFD controller, is that it pretty much eliminates the feedback current or the contribution current. Now, a secondary way of setting up a VFD drive is to use a separate. So here we've got the DC motor, a typical induction motor. These are all 150 horsepower. And then we've also set up a VFD drive utilizing a separate VFD controller. And frequently this will be used where someone wants to use a cable run or simulate a cable run between the controller and the drive motor itself. And again, in the short circuit focus, the VFD setup for non-regen will have zero contribution. Downstream of the VFD, between the VFD and the motor itself, there will be motor contribution during an arcing fault or a fault, but there won't be anything upstream of the VFD controller. Okay, so that's all well and good. Now let's go to PowerFlow. In PowerFlow, we're going to solve the PowerFlow equations, and what we see, and for the most part, I'm trying to make this similar size, and I'd expect similar results. And what I see down here on the motor itself is 100, and I'm showing the kVA. We look at the PowerFlow options. We're showing on the one line the kilowatt and kilovar on the motors and the loads and the generators. So we're showing 122.97 kilowatts and 24.97 on both of these motor connections. Now, there's a difference upstream where this is actually drawing more current. It looks like it's about 10 watts or so, 10 kilowatts or so. And I think that's a function of the losses that we're trying to simulate in the controller itself. We can see over here that we don't have any reactive power in the DC drive, and we're at the same essentially work done on the DC motor. Now, all this is being done at 60 hertz. So if we go back to our database edit and we look at the way we set up the VFD controller, we see that we're driving the output frequency of 60 hertz. We probably should have changed the voltage to 460 or so, but we're showing the power factor being elevated. As long as the efficiency and the power factor are the same, we should have the same results out from the motor that's involved in the VFD setup. So that gives us the benefit of doing a 60 hertz power factor solution, and it shows the power flow around the individual motors. We can show here we have a 1 per unit voltage in both cases and a slightly different power angle upstream of the controller, but it matches what we have set up on our two systems. Okay, so now the question becomes what happens if we're talking about a different frequency? Well, got another example set up with different frequencies and trying to do a comparison of so here we have a 60 hertz setup, a 50 hertz, and a 70 hertz. These are basically set up as you'd expect, where we're talking about the output frequency and the same power factor and efficiency. Now the issue ends up being there's a modification assumed in the power factor. When we go to PowerFlow now, we're solving the equations and we're seeing a different output below the 60 hertz, which is our baseline. We see a reduced per unit voltage to get the output that we expect. And so this is the chart that we looked at earlier, where we have a constant horsepower and we modify the power factor and the voltage to accommodate it. If we look at the scale factor that the motor produces, we can see it's running at something less than the 70 power, and if we look at the scale factor here that has been calculated, we're seeing it's running slightly scaled as far as the power factor. So this is consuming more power to run at a frequency above the 60 hertz basis. Now, so let me make a comment on that. So what we're talking about is pushing a motor that was designed for 60 hertz to a different frequency. And while that's a complicated situation, EasyPower approximates that results below. Did I have that in my? Yeah, I did. Here it is. Below 60 hertz, the VFD output power flow is the power delivered at 60 hertz multiplied by the voltage squared. So that's below 60 hertz. Above 60 hertz, it's the power at 60 hertz times the frequency over 60 squared. So let's go back and see how the tool does that. So here on the 50 hertz load, we take the power at 60 hertz, which is 122 kilowatts, and we multiply times the per unit voltage squared. And so that's 0.83, and we get a result of 84, which is very close to what we're showing on and the difference is the fact that the power scaling on the motor has been modified as well. Likewise, above 60 hertz, we take the power delivered at 60 hertz and multiply times the ratio of the frequency divided by 60 squared. So here we got 122.7 or 123 times 70 over 60 squared, and we get 166 out of that, which is very close to what we're showing on the summation. Okay, so that's again taking a motor that's designed for 60 hertz and pushing it to a different frequency. And as I mentioned, this is fairly complicated, and so it's reasonable to say that this is a good first order approximation of the results. Now, with that said, the question comes up, what happens if I have a motor designed to run at a different frequency? How do I handle that? Well, there's a whole chapter in the user's manual that talks about simulating a motor that's designed for a different frequency, and then estimating what the results will be and what the power factor correction will be at the new frequency. And the example that's being shown is if we take 110 horsepower, 110 a motor designed for 110 hertz, 100 hertz, which is going to be this turquoise line up here, which at 100% power, 100% of its frequency, it delivers 100% of or it doesn't have a need for correction. If we're going to run that at a lower frequency, in this case 60 hertz, then we have to modify the power factor correction. It looks like to be about 0.75 of what the power factor is of the motor itself. So that's what's described in this lower part of the user manual. And frankly, it's beyond the scope of this discussion, so I don't have any way to simulate the 100 hertz motor system. Now, so what have we covered? We basically talked about the setup for short circuit. It's fairly straightforward, and the only probably impact of using a VFD drive is the ability to control motor contribution to an upstream fault. In PowerFlow, it gets more complicated, and the tool can handle VFD drives at pushing to a motor to a different frequency. Now, the point I wanted to make is that what we're really talking about is simulating an approximate result based upon factors that we're, if you will, estimating. Most of these factors that are going into these calculations are controlled by the motor, the VFD controller itself. So if I know specifically what the power factor is and what the efficiency is, what the output frequency is, and the X over R that the VFD is presenting to the system, I can get a more accurate result based upon real data and not just using something that approximates using typical values from a 100 horsepower motor, which is what EasyPower does for PowerFlow. Probably as good as I can stomp on it. It's non-trivial as far as the precision, but in EasyPower, it's relatively straightforward as far as showing where the energy consumption will be improved. Normally, the power factor will be improved if I'm at the frequency for which the motor was designed. Regeneration is often beneficial when we're doing where we need to have consistent braking or assist the motor in holding a load with the power off or the control signal off. One difference that we could see between the VFD drive integrated in the motor controller and the separate AFD controller is there is some losses involved, predicted losses between the input and the output, and that's why some large VFD drive controllers need to be air cooled. And then finally, unless you have some fairly decent filtering, you're going to have the potential for line side harmonics because of the sharp rise time in the pulse width modulated signal, control signal. Okay, so that covered most of what I was trying to reflect. Certainly, if you've got other questions, you're welcome to contact easypower.com support, and we can get into the details of your particular requirement. Harold's saying, run into VFD drives that were more than one motor was driven by one VFC. How do we handle that? That's a specific case. Rather than take a guess at it, I would refer you to tech support. My first run would be integrate the total motor, because that's what would be seen upstream. Okay, so you're also saying 50 hertz motor. So the answer is yes. If you set up a 50 hertz system, I failed to mention that. EasyPower can run on virtually all frequencies between 50 and 400 hertz. And so we have some shipboard designs that use 400 hertz motors, and built into that setup will be the ability to run at 400 hertz. I don't know if I can show that without going into gory detail, but let's go back and see if we can. If I'm going to set up this motor, I'm probably going to step on myself here, but let's give it a shot. If I'm running my system at 400 hertz, the same method would apply to 50 hertz. And my VFD was going to run at 400 hertz. Then the results would be at least handled in the specs that I use for the motors. So what I'm saying is this should result in a solution. Yeah, and so we get effectively the same type of results, even though we're running at the higher frequency. William asked if the motor equations are used in the user's manual, and yeah, the description of exactly what I described is in the user's manual in the first section of that VFD section. All right. Thank you, everyone, for attending. Certainly check out the website to see what upcoming presentations will be held. And if you've got other questions, contact support at easypower.com. Have a good day.